Hello there, and in this chapter we're going to be discussing hypothesis testing. First, let's discuss hypothesis testing in regards to proportion and mean. First, let's discuss the definitions of what hypothesis testing is. Hypothesis testing is a procedure based on sample evidence and probability. It's used to test the statement regarding a characteristic of one or more populations. The steps in hypothesis testing are first, making a statement regarding the nature of the population. Then we collect evidence, which would be your sample, to test that statement. Then we analyze that data from the sample to assess the plausibility of that statement. First, what we need to do is create our hypothesis statements. You will have two. The first one will be read as H0, which is your initial hypothesis, your null hypothesis. It's a statement to which is going to be tested. The null hypothesis is a statement of no change, no effect, no difference. It's assumed to be true until we supply evidence from our sample that indicates otherwise. The alternative hypothesis, H1, or H alternative, HA, is a statement that we are trying to find evidence in order to support. In this chapter, we will have three ways in which we can set up this null and this alternate hypothesis. We can have an equal hypothesis, in which the null hypothesis is where your parameter equals some value. Now remember, the parameters we're going to be discussing are either going to be mean, or it's going to be standard deviation, or it could also be proportion. So one of those three parameters we'll be discussing, and they'll be equal to some value. The alternate hypothesis we're going to use is that that parameter is not equal to that value. A picture of this in a normal distribution curve, we would say that if the parameter is not equal to, if the parameter is in the middle and we say it's not equal to, that means it lies in one of these two tails. So either your sample was very much larger than or very much smaller than your original parameter, which was in the middle. And it has to be so far away so that that is enough evidence to conclude that your original was not true. In other words, your sample can't be close to the original. It has to be far enough away so that we can say, oh, there's enough evidence to prove that that parameter is no longer that particular value. This is what we call a two-tailed test, because when it's not equal to, we're not specifically saying that it's bigger or that it's less than. We're simply saying it's just simply not equal to that parameter which was in the middle before. Now, if you want to be more specific and state that it is less than, we would say that our initial null hypothesis, we would say that our initial parameter is equal to some value, and that the alternative, we would say the parameter is less than some value. So we're trying to prove that the parameter is now less than whatever the value was that was being claimed earlier. If we're stating less than, then we're only stating it's a left-tailed test. We're saying our sample is going to be on the left side of the average. The third option is that the parameter is greater than some value. So that would be our alternative. If we state that our parameter is now larger than what we claimed, the sample has to say that the information is greater or in the right tail of the normal distribution curve. So we have two types of curves. We have a two-tailed test, and then we have a one-tailed test. This would be a left tail, This will be a right tail. So there are 3 different types of tests that we'll be discussing. Notice that the null hypothesis is the same all the way down. It has parameter equals a value, parameter equals a value, parameter equals a value. These are always going to be equations. The alternative or the alternate hypothesis will always have an inequality sign, either not equal, less than, or greater than. You will not see equal signs for the alternate. So before we actually start solving problems, let's walk through actually a couple of suggested examples. Okay? According to the National Association of Home Builders, the mean price of an existing single-family home in 2009 was $218,600. A real estate broker believes that because of recent credit crunches, this mean price has actually decreased since this study. So let's come up with this null and the alternate hypothesis. Remember, the null hypothesis always states that a parameter equals some value. So the claim that's being made is that the average home is $218,000. We are trying to prove otherwise. So in our alternate, we're trying to prove that the mean is something different than $218,000. The question is, what sign is going to go in there? Are we trying to prove that it simply is just not that amount? Are we trying to prove that it's more? Or are we trying to prove that it's less? Well, the key word here is decreased. Because of the recent credit crunch, we're trying to prove that the mean price has decreased. So we're going to put in a less than sign. So this would be an example of a left-tailed one-tail test. Let's try another. According to the CTI, the Wireless Association, the mean monthly cell phone bill was $47.47 back in 2010. A researcher suspects that the mean monthly cell phone bill is different today. So the null hypothesis always states that the mean is equal to some value. And right here states that the mean cell phone bill is $47. Our alternate, we would say the mean is something different than that. We just have to decide what the sign is that goes in there. Well, the researcher suspects that the mean monthly cell phone bill is different today. It does not state that it is more or less. It just simply says no longer equal to. So those are the key words that you're going to want to look for when creating your null and your alternate hypotheses. This is going to be step 1 in the process of doing your hypothesis testing. Now, since we are going to be using sample data to decide whether or not to reject the statement to the null hypothesis, there is always the possibility of making an incorrect decision. So there are 4 possible outcomes from all hypothesis testing. So down here in the table, I've actually created a chart of the 4 different types of conclusions we can make. So let's say in reality, the null hypothesis is true, and let's say the conclusion, you don't reject it, so that would be the correct conclusion. You don't want to reject the null hypothesis if it is in fact true. But what if the null hypothesis is true, and then you end up rejecting it, saying it's not true, it is a false statement, when that is an incorrect statement? So you would be making an error. This is what's called a type 1 error. Alpha, which you've seen before, is the amount of error we're willing to risk in making that type 1 error. This will be a small number. Usually 5% would be the most common amount of error you're willing to make. Now there's another situation over here. What if the alternate is true? And let's go back to, well, what if you don't reject the null? In other words, your the conclusion you're claiming is that the null is true, but in reality the alternate is true. This would be an error. This is what we call a type 2 error, or beta. And then the fourth type of conclusion is if you conclude that you're going to reject the null hypothesis, you're saying the original claim is not true, and then you're claiming that the alternate then is true, that would be a correct conclusion. So you see we have two correct conclusions, two errors, but they're two different types of errors. One is willing to risk an alpha of making that error, and the other is the beta. We're going to concentrate most of our efforts on the alpha. In other words, rejecting when you shouldn't have done so. So remember from the previous example that we never quite know whether a confidence interval contains that unknown parameter. We only know the likelihood that it might capture that parameter. Similarly, we never quite know whether the conclusion of the hypothesis is correct. However, we can determine the probability of making some errors, like, for example, an error of alpha. Alpha is the level of significance, which you've seen back in Chapter 9. It's the probability of making that type 1 error. The probability is chosen by the researcher before the samples are collected. Beta is the probability of making the type 2 error, as the probability of one increases and the other then decreases, and vice versa. So let's look at an example. Let's say that we are talking about a criminal trial, and in any trial the defendant is assumed to be innocent. We give the defendant the benefit of the doubt. What would the null and the alternate hypothesis be, and what would it mean to make a type 1 and a type 2 error? Okay, so we've got a null hypothesis. The null hypothesis says that the defendant is innocent. Because we always say that they're innocent until proven guilty. You have to bring enough evidence to prove otherwise. Many guilty people are set free because there wasn't enough evidence to prove that they were guilty. So the alternate would be that the defendant is not innocent, or in other words, guilty. So a type 1 error, let's discuss that. A type 1 error is made when you conclude that you reject the null hypothesis. In other words, we're going to reject this and claim the defendant is guilty, but in fact, the null hypothesis was actually true. So we're saying the defendant is guilty, we're sending him to jail, when in fact, he was innocent. So this would mean an innocent person goes to jail. How about a type 2 error? What would happen if we make a type 2 error in the court? A type 2 error would be made if you conclude to not reject the null hypothesis. In other words, we're not rejecting this when in fact the alternate was true. So in fact the defendant is guilty, but we're concluding that the defendant is actually innocent. So you're setting this guilty person free. Okay? So there are definitely two types of errors, and both of them are wrong for different reasons. So let's look at the last example of something that you might encounter. Okay? So this was the equation that we had from the previous page. We talked about the average price of a home, which was $218,000. We already discussed on the previous page what the null and the alternate hypothesis was going to be. Remember this from the previous page. This is going on another step further. What would it mean to, after you complete your null and your alternate hypotheses, what would it mean to make a type 1 and a type 2 error with this particular example? Well, let's reiterate what my null and my alternate hypothesis was. My null said that the average home price was $218,000, and my alternate stated that my mean was actually less than that. A type 1 error again would mean, a type 1 error would mean that you're going to conclude to reject the null hypothesis when in fact the null was true. So we would reject this null hypothesis when in fact this was true. So we would conclude that the mean price had actually decreased when in fact it was still $218,000. So, in other words, we would conclude that the alternate was true when in fact the null had never changed. Now, a type 2 error, let's go back up to the type 2 error. The type 2 error is made when you conclude that you are not going to reject the null hypothesis, but the alternate is true. So that would mean we are concluding that we are not going to reject this, but this was true. So we're claiming this when this was actually true. So we did not conclude the mean price had changed when in fact it did. Okay, so we did not conclude the mean had changed when in fact it did. Okay, so let's talk about hypothesis testing of a proportion. Okay, so before we get to that, we'll do one quick example. It's also important to know how to state these conclusions. So once you find the conclusion, how do we state that in a sentence? We never accept the null hypothesis. Just like in the court system, we never accept that they're innocent. We never say you are innocent. We just say we failed to provide enough evidence to prove that you were guilty. That doesn't mean that you were not guilty, right? We just didn't bring enough evidence to the table. The same thing is true here. We never accept the null hypothesis because without having access to the entire population, we'll never know the exact value of the parameter. So rather than say we fail to reject the null hypothesis, it's just like in the court system, we never declare the defendant innocent, but rather we say they're not guilty. So we say we fail to reject the null. Instead of saying we accept the null, we say we failed to reject it at this time. So for example, the same question we've been dealing with the mean home prices. Let's pretend the null hypothesis is not rejected. Let me one more time repeat what the null was and our alternate. Okay, so I repeated our null and our alternate hypothesis. Now, let's pretend we did all of the work and we decided that the null hypothesis was not rejected. In other words, we did not have enough evidence to claim this at this time. So we're going to have to stick with this claim. We can't say that this is true. We just didn't have enough evidence to prove something different. So what we would state is even though we didn't have enough evidence to prove this at this time, the conclusion would be that there is not sufficient evidence to conclude that the mean price of a home has decreased from $218,000. So again, we don't say that the mean price is still $218,000. We are simply saying that there's not enough evidence at this time to conclude this. So what would change about the wording if we did reject? So let's say we do reject this and we accept the alternate, or we had enough evidence to prove this otherwise. We would simply say the exact same thing, but we would simply just get rid of that word not. So we would state there is sufficient evidence to conclude that the mean price has decreased. So the only thing that would change is getting rid of the not. So in the first suggestion, we do not have enough evidence, and in the next one, we do have enough evidence to conclude that. Again, we're always trying to conclude this as our answer. Okay, so we'll do more examples of that, but let's talk about what it would look like from a proportion standpoint. So let's recall that the best point estimate of the proportion parameter is going to be the proportion of a population with a certain characteristic will be given by p hat. That's coming from your sample. X will be the number of individuals in the sample that have that characteristic, and n is the sample size. Also remember that the sampling distribution of p hat has to be approximately normal. The mean and the standard deviation will be given. So we got to also provide that NP1 minus P is at least 10. That's what provides that it's normal. The random sample has to be randomly selected, and all of the samples are independent of each other, meaning N is less than 5% of the total population. So we need to prove those three things. It has to be random, normal, and independent. There are three different methods for testing hypothesis. We'll be covering what's called the p-value approach. Let's walk through an example. Let's suppose a politician wants to know if the majority, which is more than 50% of her constituents, are in favor of a certain policy. A poll is conducted as the sample proportion is found to be 53.4%. Definitely that is majority, but remember that's coming from a sample. So we want to know if these results suggest that among all registered voters that more than 50% will then favor the policy, or if it's possible that the true proportion is less than 50%. Meaning, would it be unusual to obtain a sample proportion of 53% or higher from a population whose proportion is actually 50%? When the observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant, and then we reject the null hypothesis. So to determine in this situation whether the result is unusual, we can calculate the probabilities using the normal model provided as long as we met this criteria that was above. I've created a normal distribution curve for you on the next page. So for this particular example, let's say we want to find the probability that the proportion in my sample is greater than 53.4%. So remember, we want in our population, we want to have majority of voters that feel a particular way about this politician. So we want more than 50%. We took a sample and we found the sample was 53.4%, which obviously is in the right-hand tail of this graph. So we're looking for, since this is going to be a right tail test, since it's a greater than symbol, we're looking for the right shaded area of this graph. So we would be looking for the probability that p hat is going to be above that value. So what we have to do is we have to turn this value into a z-score. Remember, to find that z-score, we have to take the true proportion of the sample, which is 0.534. We subtract that from the population proportion, and we divide that by the standard deviation. Now remember from the previous page, standard deviation was given to us by p, 1 minus p over n. So we're going to assume that there are 1,000 people in my sample. So when we calculate all of that, we find a z-score of 2.15. And we will look up this z-score in the z-table, which again is table 5. Table 5. We have a z-score of 2.15. So 2.15, we're finding a probability of 0.9846. 0.9846. But that's going to be this side of the graph. Remember, the table will only give you left of a line. In order to find the right side of the line, we have to subtract that number from 1. And then that's where this number would come from. So the value of 0.0158, which is this probability right in here, that's what's called the p-value. That's the probability value. It means that about 2 samples in 100 will give a sample proportion as high or higher than the one we obtained if the population proportion actually was 0.5. Since this is unusual, we take this as evidence against the statement in the null hypothesis. The p-value is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption in the statement of the null hypothesis if it were true. Put another way, the p-value is the likelihood or probability that a sample will result in a statistic such as the one obtained in the null hypothesis if it were true. So let's talk about all of the steps in order to do this. Using this p-value approach, if the probability of getting a sample proportion as extreme or more extreme than the one obtained in this is small under the assumption the statement in the null hypothesis is true, we will reject the null hypothesis. So below are going to be the basic steps. You're going to follow all of these 7 steps every time you do a hypothesis test. The first step is confirming that the requirements are satisfied. So we went over those requirements already. It has to be random, it has to be normal, and it has to be independent. So you have to make sure all 3 pieces of the criteria have been met. Then we determine what the null and the alternate hypothesis is and structure it and determine what type of tail you have. The third step is selecting a level of significance. Typically this is going to be given to you because your level of significance is going to be the amount of risk you're willing in making a type 1 error. If it's not given, assume it's 5% because that is the most common type of error we're willing to accept. Then we compute in step 4 what's called the test statistic using the following formula. You're finding your z. So you take your sample proportion and you subtract the proportion from your original claim divided by p times 1 minus p over n. That's your standard deviation. Remember, your sample data minus your true average divided by your standard deviation. Or you can use StatCrunch by using proportion stats 1 sample, which I'll do in a future example. Step 5, use the normal distribution table, table 5, to determine the p-value. Note the following. If you have a left-tailed test, then you want the area in the left tail. If you have a right-tailed test, you want the area in the right tail. So that means you're going to have to do 1 minus the probability to find the area in the right tail. But if you have a 2-tailed test, then you want 2 times the area in 1 tail, and this part is usually forgotten. So for example, if I'm looking at a curve right here and you go to your table and you find the area in 1 tail, well, if it's a 2-tailed test, you're going to have to multiply that area by 2 because there's another tail on this side. In step 6, we'll decide whether to reject the null hypothesis or fail to reject the null hypothesis. Basically, if the p-value is less than your level of significance, you will reject. So looking at a picture down here of what we have so far, we would draw the curve, and the alpha is predetermined by the problem. This is the probability that you're willing to make a type 1 error. We call this the reject zone. Let me color that in red. So this would be my reject zone. Okay, and that's determined by alpha. Alpha, let's say, for this example, was 0.05. So that means this area in red is 5% of the graph. So the alpha determines where your reject zone is. Now, we go when we take our sample. If we find our sample is somewhere over here, that means it's too close to the average and you don't have enough evidence to claim that the null or the parameter has changed. However, if your sample falls in this tiny little tail over here and it's far enough away from the average, well, now you've concluded that your sample is so unique that this average is probably no longer the true average. You're going to claim something different because your sample is so unique. So if my sample, which I'll do in blue, if my sample ends up falling over here and you find its z-score is over here in this reject area, you find the p-value, which is the proportion or the area of this blue tail, and if that area is smaller than the red area, you're going to reject the original claim in the null hypothesis. However, if the p-value is large, meaning this blue area is large and your sample was close to the average, well, then we fail to reject the null hypothesis because your sample simply was not unique enough. And that's when we state the conclusion. Do we have sufficient evidence or do we not have sufficient evidence? And it talks about how to state that in a sentence here. We either have sufficient evidence at a % level of confidence to conclude whatever the alternate is, or we do not. So let's run through a full example of this and let's use all 7 steps. And as you get better at this, you'll learn how to shorten your steps, but it's best to do them all 7 until you get used to doing this. Okay, so let's start by labeling step 1. The drug Lipitor is meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of the 863 patients taking... My apologies, I didn't have the right question down. This question is about the drug Lipitor, and it's meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of 863 patients that take 10 milligrams of Lipitor every day complained of flu-like symptoms. Suppose that it is known that 1.9% of patients that take competing drugs complain of flu-like symptoms. Is there evidence to conclude that more than 1.9% of Lipitor users experience these flu-like symptoms as a side effect? And let's use the 0.01 level of significance. So if we recall back to our 7 steps, the first step is to state your null and your alternate hypotheses. Actually, that's step 2. Step 1, first, do we meet the requirements? I'll come back to that. Do we meet the requirements? The requirements are, is it normal? To determine if it is normal, we first have to decide if n times p times 1 minus p is greater than or equal to 10. Well, in this case, n is given to us through the question. There were 863 patients in the study. P is given to us in the study. It says 1.9% of patients taking competing drugs complain of these flu-like symptoms. So 1.9% is our P. 1 minus P, and that's equal to 16.1, which is indeed greater than or equal to 10. So we can include that this definitely is normal. We also have to state that the sample was randomly selected. So if it doesn't state up here that those were randomly selected anywhere, we have to assume that this is true. Lastly, we have to prove that the sample is independent. In order to prove that the sample is independent, the sample has to be less than or equal to 5% of all people in the population. Well, certainly the N, which is 863 patients, is certainly smaller than 5% of all users. So we'll assume that is also true. So we're making those assumptions. Finally, step 2, which I started to do, this is where we make our alternate and our null hypotheses. Now remember, your null and your alternate always start with mu. Your null will have an equal sign and your alternate will have something different. And then they'll both have the same value. So for this one, we're talking about proportion. So we're not starting with mean, we're talking about proportion to start. In the next section, we'll talk about mean. So for now, let's talk about proportion instead of mean. The proportion that we're discussing here is 1.9% experience flu-like symptoms. So the claim that is being made is that the true proportion of people that feel flu-like symptoms is 1.9%. We want to conclude something other than that. What kind of sign will we put in there based on the question above? We're trying to conclude, is there enough evidence to conclude that more than 1.9% of Lipitor users will experience flu-like symptoms? So we're trying to prove that more than. In step 3, we discuss what is the level of significance. The level of significance will always be given to us. This is the amount we're willing to risk in making a type 1 error. We're willing to risk 1% chance. Then we look for our test statistic, Z. Z is equivalent to p hat minus your original p over p times 1 minus p over n. Your p hat is given from your sample. Your sample from this example was 19 out of the 863 patients experienced flu-like symptoms. So let me go off to the side real quick and let's calculate what p hat is. P hat is going to be 19 out of the 863. 19 out of 863 is 0.022. So our point estimate is going to be 2.2%, which certainly is larger than the rest of the competing drugs and their flu-like symptoms. So it looks like, at first glance, it looks like Lipitor does cause larger amounts of side effects of flu-like symptoms. But it's pretty close. So is this far enough away from the claim to conclude that this is true? Or is it too close that, well, we really can't conclude anything is different than what it was originally claimed to be? So we're going to take that information, we're going to run it through the test. P hat is 0.022. And then we subtract the original p of 0.019 divided by square root of 0.019 times 1 minus 0.019 all over n, and in this case n was 863. And make sure all of that is under the square root, including the denominator. Now it takes a little practice putting all this into our calculator, but you're going to get, hopefully, that the z is going to equal to 0.649. And this is what we call the test statistic. And it's a statistic because it's coming from your sample. So then what we do is we go to table 5 and we look up the probability of that occurring. Okay? So let's first look at a curve and determine what we're looking at with the curve. Okay? So I've got a curve down here. And I know right down the middle I have my true proportion of 0.019. I also know that my reject zone is 1%, and this is a right-tailed test. So this is going to be my reject zone because alpha is 0.01. I'm looking for this probability right here. I have a z-score of 0.649, and I want to find out where that lies down here so that I can decide if that lies in this reject zone or not. So I have to first find the probability of this z-score. So I'm going to go to table 5 and I'm going to look up this z-score and find the probability. 0.649 for a z-score. 0.649 would be closest to 0.65, and that's going to give me a probability of 0.7442, or excuse me, 0.7422. 0.7422. Now remember, that's going to be the probability of the left side of this graph. I want the right side, so I have to subtract that from 1. So I get a probability of 0.2578. And so if I were to drop that on my graph, 25% is certainly larger than 1%. So over here is going to be my test statistic. This is going to be my p-hat. P-hat is 0.022, which has a z-score, which has a z-score of 0.649, which in turn has a probability or a p-value of 0.2578. So you're going to see that our sample in blue is not unique. If it were unique, it would be farther away from the average and it would be over here in the reject zone. Since this sample is not in the reject zone, it is not far enough away, we're going to end up not rejecting the null hypothesis. And that's where step 6 comes into play. Step 6 says compare. Compare your p-value to your alpha. In this case, our p-value obviously is much, much larger than our alpha. And when your p-value is larger than your alpha, we fail to reject the null hypothesis. So in a conclusion, how I would state my answer, I would say there is not sufficient evidence to conclude at the 0.01 level of significance that more, and this is where we put in the alternate, that more than 1.9% of users experience flu-like symptoms. So there are a lot of steps, and we're going to do this a few more times, and it's going to take some practice.